Hey everyone, and welcome back to Summarize Science. Today, we're diving into a paper that tackles a huge problem with some of the most powerful AI models. Imagine an AI that can look at a few pictures of an object and instantly create a detailed 3D model of it, just like you see here. That's what a model called VGGT, or Visual Geometry Grounded Transformer, can do. But there's a catch. This AI is massive, with over 1 billion parameters. Running it requires a ton of computational power and memory, making it impractical for devices like your phone or a drone. The goal is to shrink it down using a process called quantization. Think of it like converting a giant, high-resolution photo into a smaller, compressed JPEG file. You lose a tiny bit of detail, but it becomes much easier to handle. However, standard compression techniques don't work well on VGGT. This is because it has special components that create huge, spiky outliers in the data, which you can visualize in this diagram. Trying to quantize this is like trying to neatly fold a blanket that has a few pointy rocks hidden inside. So, the researchers developed a brilliant two-part solution called dual-smooth fine-grained quantization. First, they use a clever mathematical trick called a Hadamard rotation, which you can see in action here. It essentially takes those data spikes and spreads their energy out, making the whole distribution smoother and easier to compress. Then, they apply a second smoothing step to balance everything out at a finer level. Their second innovation is how they calibrate this process. Instead of just feeding the model random images, they created a system to filter out noisy or unhelpful examples. It then clusters the good data based on the AI's own understanding of geometry, ensuring the calibration set is diverse and representative. So, what are the results of all this hard work? As this table shows, the new model, QuantVGGT, is incredibly efficient. At the 4-bit level, it achieves a 2.5 times speedup in processing and a 3.7 times reduction in memory usage. And the best part? It does all this while maintaining over 98% of the original model's accuracy. As you can see in these visual comparisons, the 3D reconstructions from the tiny, compressed model are almost indistinguishable from the full-precision original. So let's recap the key points. Researchers took a powerful but enormous 3D vision AI and needed to make it smaller and faster. They overcame the failure of standard methods by designing a custom dual smoothing technique to handle data outliers and a smart sampling strategy to ensure stable compression. The result is a model that's drastically more efficient without a noticeable drop in quality. This is a huge step forward because it could unlock the power of high-end 3D reconstruction for everyday devices. Imagine apps on your phone that can instantly create a 3D scan of a room, or drones that can map environments in real time for rescue missions. That's the future this research helps make possible. Thanks for watching Summarize Science. We'll see you in the next one.